real important. We've been working up to this point, really, until this day. Everything has been building until this point. We've been talking about plate girders. First, I guess we started out with rolled sections. We reviewed those and talked about those. Then we got into plate girders and started talking about more details about those. Now, what is the goal with a plate girder? Why would anyone want to build a plate girder? Why wouldn't you just use a rolled section? What are the benefits of the plate girders? You can optimize your web is probably the biggest one. Really skinny down areas you don't need, right? And webs happen to be the section that's most often skinnied. Okay? It's a technical term, skinnied. It's in the steel manual. You have to look in the glossary. Okay, it's there. Anyway, it's not. Anyway, so that's what plate girders are all about. And we've said, really, that there were 4 charts that explained all of the behaviors of plate girders. Talked about all the behaviors of plate girders. And what do the charts look like? Snails, right? They all look like snails. Okay, and we'll talk about our one that we're most common with, the one we introduced as undergrads, and we had FEMN, and we're going to have FEMN on 3 of these. 3 of them, but not on the 4th. And then what's the Xaxis on the one that we're most familiar with, the one we've done the most work with? LB. LB. Length between the braces, the unbraced length. Okay, talked a lot about that in this class. Okay, then we have another one, and it looks like a snail too. It looks a little differently. Now, I'm not saying these can be overlaid, because you can't even really compare them, because the X-axis is totally different for this one. Who remembers what it is? Anybody? Slenderness. Man, good answer. A gamma, right? And I wish they would pick different gammas. Okay, I wish they'd pick different sections, but I didn't invent it, and so therefore I didn't get to name it. Okay, so it doesn't go in there. So that's my tip to you today. If you don't like the names of something, invent something better, right? Then you can make your own name. It's a gamma. It's a slenderness. That's exactly right. And we'll say it's the one for the flanges. Do you remember what the gamma means for the flanges? What's the equation? It's important. So flange. What would we compare in a flange? What is the critical aspect of a flange? We talk about it getting slender. What's that? Thickness. And what's the other one? The width. The width. And usually, typically, when we think of a W shape, truly, we're thinking of this width versus this thickness. You with me? But they don't do it that way. Because in the steel manual, they don't give you this width. They give you this width. It's B sub F. You with me? So this gamma is B sub F over 2 T sub F. Why is it over 2? Because there's 2 of these things. Okay? T sub F, that's the thickness of the flange. You're with me? Oh, yay. And it's the same thing. And we've got something called a gamma sub P. We've got something called a gamma sub R. And in past notes, you can dig for these. You can find these. I've given them to you. I've given you there's a table in the manual that has all of these laid out. I've talked about those. Okay? There's a gamma sub P and a gamma sub R, and they're different for different shapes. Because not everything's a W shape. Sometimes we have channels. Sometimes we have T's. Sometimes we have singly symmetric members. Okay? So, there's different ones for different situations. Okay, we got another one. Guess what it looks like? A snail. How did you ever know? Because they all look like snails, right? So there's a flat portion, a linear portion, and a non-linear portion. Hey, so what is the y-axis down here, or the x-axis, pardon me? Slenderness. Good answer. That's right. It's exactly right. It's crazy. It's crazy, but it's right. Slenderness, but it's a different slenderness this time. What are we worried about? What are we looking for? What's the third Snail Chart of Apocalypse about? The web. That's right. So what are the key variables in the web? What do you think? The thickness and the what? The height. It can be louder, okay? Cyberspace can't hear very well, okay? So you got to let them know you're there, all right? I mean, this is your chance. You realize what opportunity you have? This is your chance to go down in cyberspace history. We're like, man, I don't know who that person was, but their voice is so smart. Okay? They got so many of those answers right. Okay? Okay. I can go the other way too. Be like, those people that year were so dumb. They didn't know any of the answers. Okay? Come on. Come on. 2012, make your mark, right? Okay, so you're exactly right. It's the H over the T sub W. H over T sub W. And what are these things? Gamma P, gamma R. I don't know why they didn't name them something different. But they didn't. They didn't do it. Hey, before we go on to our fourth Snail Chart of Apocalypse, we got to this one. Okay? What is the C sub B factor? What does it do? What's that? Increases capacity. There you go. Increases capacity. All the way around, right? Up here, right? No. Where does it increase capacity at? Only for lateral torsional buckling. So our C sub B comes somewhere out here, and it's caps. Right? Remember that? Okay, we're going to come back to that in a second. Now, our fourth Snail chart. What is the y-axis? C sub V. C sub V. And what is C sub V? There you go. That's right. It's a reduction factor, and it really tells you a ratio of T critical or tau critical, the yield, the shear, critical shear stress versus the yield shear stress. And this value, this T sub y, does anyone know what that is? 0.6 Fy AW. You with me? So what's common is to express this as phi Vn is equal to phi 0.6 Fy AW C sub V. C sub V, all it's going to do is reduce this. You with me? Makes sense? Okay, we're going to come back to this equation in just a second. Okay, so what's this final Snail chart look like? A snail, of course. It's got a flat part. It's got a linear part. And it's got a non-linear part. But this is different. It's not phi mn anymore. It's C sub V. And what's the maximum value up here? Does anyone know? 1. Very good. And what is the x-axis? Slenderness. Smart. Yeah, that's right, you smarty. That's right. It's slenderness. And what is the slenderness? For what? The web. It's the same as this, isn't it? It's the exact same as this. H over T sub W. The exact same. Now, when we do these, all of these have to do and control bending. They control bending. Mess with bending, are all about bending. And this one is about shear. It's about shear. Great. Cool. And there's going to be, guess what? A gamma sub P and a gamma sub R. Now, I'm telling you, it's extremely important to understand what it is you are doing, especially when you're an engineer and you're doing these calculations. If one didn't understand this, then plate girder design can be nightmarish, because it's like you don't really understand anything. You don't understand what you're doing, why you're calculating. You're just doing numbers, okay? And it can be extremely scary because you don't really have a feel for what's going on. And it's still scary, but it's a little less scary if you know what the playing field, you know kind of where you're at. Does that make sense? Now, whenever we deal with any of these three snail charts, and we're in this zone, what is it called? We would say our flange is compact. And if you are in this zone, you would say your flange is non-compact. That's right. Really complicated terms here, right? Non-compact. And the final zone, slender, right? And you can tell that engineers are not very creative, because if you come around to this chart and you get in this zone, what's it called? They're all the same. Come on, engineers. You can't think of some new names to call it, right? Call it Phil and Lil and Sue or something, right? Make it somewhat interesting. No, it's compact, non-compact, and slender. But that's okay. It's cool. That's cool. Standardized names, okay? Standardized names. So whenever you hear someone say, I have a compact flange, you know exactly what that means. Boom! I'm in zone 1. But I have a non-compact web. Boom! Now, you got to be a little careful here. Because when it comes about webs, you have to ask them, is that non-compact with respect to flexure or non-compact with respect to shear? Because even though these are both the same slenderness ratios, even though these things are called gamma P and gamma R, they're not the same gamma P and the same gamma R. You with me? I don't know why they call them all the same. They were trying to make it not confusing, but in my opinion, they made it more confusing. Okay? So, you'd say when it comes to the web, it's non-compact with respect to flexure, but compact with respect to shear. You with me? When people call those out, they mean things. Now, let me give you a piece of advice. Whenever you're ever doing a plate girder, a design, an analysis, whatever, figure out which zone you're in. Okay? That should be your first step. Because then if you start to make decisions, like, let's say I'm here, and I'm going to change the size of my flange, okay? That's going to have a linear impact on my moment. Linear, somewhat linear. But if I'm down here, I am off the edge of the cliff, ladies and gentlemen. And small changes in my flange can make huge impacts on my moment capacity. Does that make sense? Okay? Okay, another piece of advice. If you can avoid using a slender web, that is usually a very good idea. Usually. Usually. Not always, but usually. And what we're going to find is I'm going to give you, I'm going to tell you today, hopefully get to the point today where we know how to analyze or calculate the capacity of a plate girder. Okay? It's not that hard to analyze. And then we're going to talk about design. And design literally could be the most nightmarish experience you've ever had in your entire life if we didn't have some very, very nice equations that help you get started, and if I didn't give you a nice strategy on how to design plate girders. But with these cheat sheet type equations, I mean, they are amazing. I mean, they are worth the price of this class alone, how much money they can make you. Okay, it is awesome. Okay? With the equations and with this like method forward, you can design plate girders really quickly. Okay? Really, really quickly. You know what's going on. Okay? All right. Is everyone with me on this? Okay. So we've talked about these different zones. We've kind of reviewed these different snail charts. We've talked about what's important about them, what's kind of strange, what's not strange. And the last thing I meant to go back to here was when I get above gamma sub p, all I'm doing is reducing my shear linearly. And we can reduce some shear linearly, and that's not that big of a deal. We showed previously that like an 80% more shear than we needed on that example problem. You can live in this zone, okay? It's just when you start to drop down here, the bottom drops out real quick, okay? And you really start to impact your moment as well, a lot, okay? Something to keep track of. And it'll start to throw you into a whole separate set of equations once you jump down here. And those equations are just very punitive because AIC gets very scared when you get down here. I mean, think about it. As you get closer and closer to the edge, you want more and more of a safety factor, right? You want more and more conservativeness. Okay. What happens when we take into account tension field action? Oh, what is tension field action? That's right. It's whenever you have a girder, we're dealing with something with a slender web, we're putting it in shear. We would say the first failure mode, if this is going to have some compression, and this has to have tension over here, we idealize it as a strut in this direction and a strut in this direction. We would say the first event, because it really truly is an event-to-event analysis. I mean, it really is. I know we talked about it with beams, but you had a homework on event-to-event analysis. Truly, the first event is the buckling of this member right here, right? And it looks something like this. We showed the sandwich bag, right, where we racked it. Okay, it looks something like that. It's where there's a bend or a buckle in the plate, right? But it's not over, right? Tension field action is really just another way to talk about structural resiliency applied to webs and buckling, is that this thing isn't going to fail until this member is at its yield. Okay? And that's tension field action. So when can you not use tension field action? Don't remember, huh? Right here. The A, B, C, and D rule. Have to satisfy these rules. Now, that doesn't mean that you truly need to satisfy these rules for the physics to work. You have to satisfy these rules because AISC has made your life so much easier, making all these assumptions. Okay? And you have to satisfy these assumptions to meet AISC's simplifications. One of the biggest ones, and I'm telling you right now, people are going to forget it on the test, is that the last panel, you cannot use tension field action. Not allowed. So what do? You just allow the buckling to occur. Just allow the buckling and nothing else. Okay? When A over H is greater than 3, when this mumbo jumbo or when this mumbo jumbo is true, you can't use tension field action. What's that mean? It means it has no shear capacity, right? No. It means that we can only take into account the compression failure. We don't feel confident enough either in the ductility, its ability to bend but don't break and ask for help from the other member, or we've just made some assumptions in the math so that we have to force these to occur. You with me? Awesome. So what does tension field action do to this? This Snail chart. What does it do? Increases the shear capacity. It's kind of similar to the C sub B factor. Except for the C sub B factor was a linear offset. Okay? And we're going to find out that this one's a little bit different. This is a different line, linear line, and this is a different linear line up here, or non-linear line up here. It's a little bit different, but it's a similar type concept. Similar type concept. Okay? Alrighty then. So, at the end of class, last time, we'd gotten to the point where we started to size stiffeners. And I will be really honest with you. Okay, I don't believe in pulling punches in this class, at least, right? I lie to you in all my other classes, but not this one, right? This is an area that needs more work. Okay? The manual is not solid in this area. Okay? Not that it's dangerous, but if weird things start happening with these equations, chalk it up to the manual's still working on that. Okay? And there are things like that in science and in engineering where we're not totally sure exactly what's going on. We're still working on it. And the bad thing is that this is talking about stiffeners. And what do we know about stiffeners? No one designs them. They just pick them. Okay? So because of that, there's not a lot of concern for actually designing them, because nobody does. Does that make sense? Okay. There's not a lot of testing that's been done that really does a good job of explaining this. Okay? So this is an old equation, okay, that is not in, I don't even think it's in the manual anymore, but I've included it in my notes because I've still seen it control a couple times. So I still use it. Okay? But it's pretty easy to do. You plug in, these are all constants. These are all easy. And the biggest weirdness is this D sub S term. Okay, it's 1 if you have stiffeners in pairs, 1.8 if you use an angle, it's 2.4 if you only have a single stiffener. Okay, that's cool. I've seen this equation come up negative before. Okay, happens sometimes. I mean, what's drilling everything here is your thickness of your web squared times 18. Thickness of your web squared times 18. Okay, sometimes this turns out to be negative. If you're really getting high loads, then that's not the case. Okay? Great. But this is supposed to take care of the strength requirements. And if you don't meet, if there's no strength requirements, then you only have stiffness requirements. Okay? Remember, there's always a strength and there's always serviceability. Have to satisfy both. So this is one of the requirements, and I've also seen this equation go negative before, or be really, really small. Okay? And the way this works is you use this B term, and it's the smaller dimension of A and H, okay? And you plug in here, this is the J term, 2.5 A over H squared minus 2 less than or equal to 0.5. And this gives you the moment of inertia of the stiffener about the centroid of the web. And this is just a little weird, but what you do is you imagine, this is a plan view looking down, okay? So if I had a girder here, and it had a stiffener in it, and my eye was above, looking down on it, it would see one of these two things. Okay? It's looking down, and it sees this, and what you're going to do is you're going to find the moment of inertia of the stiffener about the web. Okay? Moment of inertia of the stiffener about the web. It's just 1/12 BH cubed, where B is the width of the stiffener, H is the height of the stiffener. Easy. And then if we have something like this, only a single-sided stiffener, it's the same thing. 1/12 BH cubed, but then we get an ADY squared term. Well, why? Because the centroid is off the center, right? Off the center of the web. Okay, cool. Now, this, in the 13th edition of the Steel Manual, this equation was in there. And this equation was kind of one of those people laughed about, like, how did that guy's equation get in there? That thing never works, okay? But it was in there, okay? And then they recently changed it. And that leads me to the handout that we're going to talk about today. This equation has been changed. It's a little bit different now. And what this equation is done is, imagine if all those minimums and all those other previous stiffener equations were derived as if you chose a stiffener spacing that was right up against the maximum. So let's say you did some calculations. We're going to work an example problem that's going to show you. Let's say you did some calculations and you found out you needed a stiffener spacing of 36 inches. Or let's just say it said 37 inches. And what did you choose? You chose 36 because it's much easier to lay out 36 than it is 37. Okay? About the same. Okay, maybe that fits the girder, the spacing on the girder, so they're equal amounts, right? All those stiffeners are at equal spacings or something like that. So you chose 36. You chose some number that's really close to that. If you do that, then all previous equations were great estimates. Estimates of how much strength and stiffness you needed from your stiffeners. Okay? This equation was derived so that if you got a little wild hair on you and you said, you know what, I might need 37 inches, but dang it, I'm going to choose 24. Maybe that's what you needed. Maybe there was some other bracing connection you needed there. Maybe 24 fit better. Maybe you had a whole pile of stiffeners that you wanted to use, so you chose 24. Maybe you just felt funny that day. Okay? 24. Okay? If you do that, then you're breaking a lot of the previous assumptions that have a very, very large panel. The largest panel that one can have. And this equation was derived so if I squish my panel down, I would expect to need a little bit more oomph in my diagonals. Okay? Alright. This equation's complex, but it's a linear, it's basically saying this reduces the IST1 and IST2. Well, IST1 is the same equation we had on the previous page, no difference. And the IST2 is this beautifully empirically derived equation. Anytime you see something to the 1.3 and 1.5 power, that is not real. That's statistics. Okay? That's a curve fit. It's not a mechanistic. Okay? It's just did some data. Or, my favorite, we ran thousands of finite element models and we fit curves to it. That's also done often. I think that's how they got this equation. Okay? So that's what the numbers are from. Okay, and it's IST2, H, that's just the depth of the web. PS2 or rho S2 is just, it's only if you have girders with different yields in the web and in the stiffener. Okay, not sure why you do that, but you might. Okay, 40 is 40. FY, that's the yield strength of the web, 29,000 KSI, all to 1.5 power. Not a very hard thing to deal with. But that is your IST2. Okay? And what you'll find actually in this equation, and we'll see it in our example problem that we're going to work today, is that if you choose your stiffener size to be really close, really close to what you need, then this turns it goes away, these cancel out, and you're left with only IST2 controlling. Can you see that? This is going to turn to 1. What's this? Well, this is your shear capacity minus your capacity with non-tension field action, divided by the capacity with tension field action minus the capacity with non-tension field action. Okay? So if this is very similar to this, and this becomes 1. The shear you're designing for is close to the shear you're providing. That's only the case when your stiffener spacing is very close to what you designed. Now, if for some reason you back it off, so you're going to jack V sub 2 way up, going to make it a lot larger than what you need, and that will change things. Does that make sense? Okay. Oftentimes, if you took nothing else away from what I just said, if you choose your stiffener spacing closer to the requirement, this equation dictates your minimum stiffness. You don't have to calculate anything else. And not calculating things is nice. Great. This is just V sub C1, the shear capacity for non-tension field action. V sub C2, the shear capacity for tension field action. That's what this is all about. Who cares? No one designs stiffeners anyway, right? Oh, well, let's do one. Let's do a stiffener design example problem. Awesome. So, this is a design problem because we've been given this section and we're going to find out ways to come up with this next time. But we're going to force the stiffeners to make it work, to provide the capacity we want. So if I have 280 kips, that's a factored load, and I find out that I'm going to need some stiffeners, okay? Then the very first thing I'm going to do is what? I'm going to find data that I need to enter table 317A and B. Remember 317A and B? Crazy awesome tables. And remember, why this is so hard is because as you change your H over T sub W and your A over H, everything else changes. So what we're going to do is we're going to fix some things, and we're going to figure out ways, not today, next time, on how to fix this geometry, how to come up with this geometry beforehand. Not saying we won't go back and iterate on it, but how to come up with a really, really good guess. Okay? Start out. Great. Okay, so we got a beam with a load in it. We're going to find our y value and our x value of our axes here. And h over t sub w, that's 120. My other axes is oh, I lied to you. We're going to find h over t sub w, and we're going to find this value first. Phi vn over aw. Okay? Okay? So I find this value, and I get 18.67. So let's do this. I'm going to go over to 18.67, and the other one's 120. 120. 18.67. Something like right there. Okay? Okay? Oh, you're looking confused. Well, this curve is 18. This curve is 21. There are 3 KSI difference between them. So if I go to the third point in between these two things, about 3 squares over, 1, 2, 3, or 4 squares over, that would be 1. If I go about 3 squares over, that's going to be about what I'm shooting for, about that data point right there. So I take that down to the x-axis, crash down to the x-axis, and I'm going to read off the value. It's going to be around 1.6. Hey, look at that. 1.6. You with me? Not hard. Crazy useful. Great. So now we know our A over H is 1.6. I already know what my H is. It's 30. I get my stiffener spacing 48 inches. It does not always come out to be a nice round number. But in example problems, I have ultimate power. Right? Great. 48. So I know now where my stiffeners go, except, you know what? I left something out. Which table did I use? Am I going to be able to use tension field action in every single place in my beam? No. Where can I definitely not use it? The last panel. So technically, I would need to do this all again on this chart and figure out what my spacing would need to be for that last panel. Would you expect that spacing to be larger or smaller? Shouldn't it have to be smaller? Because we're not going to get as much benefit from the tension field action. So we're going to need things to be closer together to keep the embrace length or the buckled length smaller. Yeah? Okay. I didn't do that. But you need to on an example problem. So we'll say this. Redo for last panel. And it's also possible, actually I should go ahead and recheck all that rule A, B, C, and D that I showed you. And make sure that I satisfy all 4 of them. Because if I don't, I've already assumed by using 317B that tension field action is going to work. Make sense? Okay. So we keep going. Calculate this stiffener area, and guess what? It comes out negative. Also, just for kicks, it's not just for kicks, it's a good idea to go ahead and plot the Snail charts and see where you're at. Now I'm just dealing with shear, so I only plotted one of them. Okay? But I found out that with this scenario, I am down here. Okay? And since I was down here, that's probably what drove me to use stiffeners in the first place. Here's how I calculated my case of V. There's my gamma P. There's my gamma R. There's my gamma, 120, and 120 isn't even close to 87. Now notice, one thing that's a little insane about this is that you need to know your A over H to find your K sub V. And you need your K sub V to find your gamma sub P. And I think gamma sub R as well. So you don't even know what this diagram looks like until you've already chosen what your stiffener spacing is. Does that make sense? I wish it wasn't that way, but that's what it is. So in a sense, we assumed we were slender. We found out the stiffener spacing we needed to make it satisfactory. We checked our assumption here. We found out that we are indeed in this zone. So that was a good assumption. This will be much easier when it comes to plate girder design because we're going to force things to be in different zones. Okay, we're going to use some tricks to force things to be in different zones. Great. So we get our gamma, calculate our C sub V, we get 0.42, and that was actually needed here. But we found out we need a negative stiffener area. That means the minimum stiffness requirements will end up controlling. That's what that means. Flip it over. So now we start solving for our other stiffness. And this stiffness was the same thing as IST1. And if we recall, the true equation for IST1, oh, it's right here. Yay, me. Put it on there. That's IST1. And it's actually a standalone stiffness. Okay? We found out when we go to calculate J that we got a negative value. That means it does not control, and we force IST1 to be 0. So then we go back to this equation, the big nasty equation I introduced today. And we solve for IST2. And finally, ladies and gentlemen, we find a positive number. Yay. But look at the value. 1.54 inches to the fourth. Okay? I could sneeze and get that. Okay? It's nothing. Okay? Nothing. But we'll keep going. So we do our shear capacity is 140. We calculate what our V sub C1 is. We calculate what our V sub C2 is. And look at this. They're almost the same. Why? What was needed, right? That's exactly why. Because the stiffener spacing was so close to what was needed. These two are close to one another. So when we work this out, we find out that this is 1. Or really, really close to 1. We find out that ends up controlling 1.5. So we just need 1.1 inches to the fourth. This is a joke. I'm just showing this just in case you needed to do this. It's very, very common to make your stiffener the same width as your flange. Extremely common to do that. To make your stiffener the same width as your flange. Look at me like I'm crazy. To make your stiffener the same width as your flange. Very, very common to do that. Extremely common. I'd argue if you didn't do that, people would wonder why. You'd get calls. Why didn't you make it the same width? When you get the stiffener, you have to clip this out. Does anyone know why? You can't weld through it. Actually, hopefully the weld's there before you put the stiffener on. But that weld still has to be there. You don't want to intersect that weld with your stiffener weld. This weld's going to have a lot of fatigue on it. Okay? you want to keep your stiffener welds away from that weld. Do not ever let anyone intersect those welds. Okay? Okay.
Why would you take that all the way down to the bottom?
It's harder to build that way. Why take it to the bottom? I guess I could ask you that question. It's pretty common to leave it a couple inches short. It's just much easier to build. Sometimes that's not capable. Sometimes you're wanting to stop some kind of movement of the top flange and the bottom flange, and you will have to go ahead and take that all the way to the bottom. What's commonly done then is you don't require, well, I don't require it to be welded down there. It only bears. So you weld at the top, you weld at the bottom, and you let it bear on the bottom flange.
Why wouldn't you weld at the bottom and let it bear on the top?
You could do that too.
Since welding upside down is more hard to do.
But in the shop here, they'll flip the whole girder over.
Shop welding.
Right.
Never mind.
That's right. That's right.
Do you increase the height of that, or would you
We're coming. We're coming to it. We're coming. But actually, none of this tells you anything about height. Okay? We do this. We'll go ahead and calculate the B that we need, the thickness that we need of the stiffener, and it's like 0.01 inches, which is like a joke, right? So you can get away with an eighth. Okay, whatever you can use to put your weld on, whatever your minimum size to put your weld on. Does that make sense? What we'll find actually coming up is that the stiffener size isn't that big of a deal. It's all about the welds. How many welds are there? How long are they? That's what's going to cost a lot of money. Now, was there something else people wanted to say or ask about this? You asked about height. You always have to think about what is the stiffener for. And this stiffener's job is to keep the web from buckling. So it would be totally wrong to leave that stiffener very short because it could still buckle below it. So in that case, you're going to want to go at least past the 3/4 point of your web. But you don't have to take it all the way to the bottom. But again, it's important to understand what your stiffener is doing. So I do not recommend welding all the way around on your stiffeners because you'll end up making your welds will fight one another. Sometimes you'll break one, and sometimes you'll cause imperfections or cracks in welds. Because you'll make this weld first, and you'll make this weld second, and maybe they'll cool differently, and they'll actually pull themselves apart. Does that make sense? So you always weld on your web. You pick a flange that you're going to be up against, and you weld on that. If you absolutely have to take it to the bottom, you make it flush, and I don't usually require them to weld. Okay? Anything else? No?